That bridge you drive over every day, it's not designed to barely hold your car. It's not designed to barely hold traffic. It's not designed to survive a calm, sunny afternoon with everyone following the rules. It's designed to hold way more than it ever should. And that's not laziness. That's not waste. That's engineering, on purpose. By the end of this video, you'll understand why engineers almost never design things to be just strong enough, why extra strength is deliberately built in, and why what looks like overkill from the outside is usually the reason things don't fail. The just enough idea. At first glance, overbuilding sounds inefficient, even irresponsible. If a beam needs to hold 1,000 kilograms, why not design it for exactly 1,000 kilograms? Why spend extra material, extra money, extra effort? From the outside, it feels obvious, like ordering a truck to deliver a single envelope. And honestly, that logic makes sense, until you realize something important. Real life is messy. Engineering includes assumptions. Engineering calculations are built on assumptions. How heavy the load is, where that load sits, how evenly it's distributed, how fast it's applied, what the material quality is, what the temperature is, how old the structure is. Those assumptions aren't mistakes, they're necessary, but they're still assumptions. Because in the real world, loads move. People misuse things. Someone parks where they shouldn't. Someone stacks more weight than expected. Someone drives a truck that's heavier than the sign says it is. Weather changes, materials age, and time quietly chips away at everything. So if you design something to survive only the perfect scenario, it will fail the moment reality shows up. Engineering equations assume a perfect world. Reality does not. Why safety factors exist. Here's a simple example. Imagine a beam rated for 1,000 kilograms. Exactly 1,000. No extra margin. Now imagine someone puts 1,050 kilograms on it. That's only 5% more. 5% doesn't sound scary. You wouldn't panic if your phone battery dropped by 5%. But structures don't care about vibes. They care about limits. That extra 50 kilograms could be enough to push stress past a critical point. Or if the beam has a tiny defect, or if it's cold, or hot, or old. And suddenly, just enough becomes not enough at all. That gap between clean math and messy reality is where overbuilding lives. This is where something called a safety factor comes in. A safety factor is simple. If a part needs to hold 1 unit of force, engineers might design it to hold 2 units, or 3, sometimes more. So if the expected load is 1,000 kilograms, or around 10,000 newtons, the structure might actually be capable of holding 20,000 or 30,000 if it has been built with a factor of safety of 2 or 3. That extra strength is a buffer, not because engineers don't trust their math, but because they do trust reality to be unpredictable. And here's the key part. Safety factors are not random. They're chosen deliberately. Different things get different margins because failure has different consequences. Take a chair. If a chair fails, that's embarrassing, maybe painful, but you stand up, you laugh it off, you blame the chair. Now take an elevator cable. If that fails, embarrassment is no longer the issue. So elevator cables are often designed to support 12 times the maximum expected load, according to ASME. Not double, not triple, 12 times. That means if an elevator is rated for 1,000 kilograms, the cables might be able to hold 10,000 or more, which gives a factor of safety of 10 at least. Is that wasteful? Only if you think falling is optional. Airplanes follow the same logic. Aircraft wings are designed to bend dramatically without breaking. In testing, engineers literally bend wings until they look wrong, uncomfortable, like they're about to snap, and then they keep going. Because a wing that survives extreme conditions on the ground has a much better chance of surviving turbulence, fatigue, and years of flight. Safety factors exist because failure isn't always equal. Materials are not perfect forever. Another reason engineers overbuild is less comforting. Materials lie. Well, sort of. Steel isn't identical everywhere, even within the same batch. Concrete can have air pockets you'll never see from the outside. Wood has knots, grain direction, and hidden weaknesses. Even with modern manufacturing, no material is perfect. And manufacturing itself introduces tiny flaws, microscopic scratches, tiny voids, small inconsistencies. They're so small, they feel irrelevant. Until they aren't. Because here's the scary part. Failures almost never start big. They start microscopic. A tiny crack forms at a defect. Stress concentrates around it. That crack grows a little with each load cycle. 1 cycle does nothing. 10 cycles do nothing. 1,000 cycles do nothing. And then one day, without warning, the structure fails. Overbuilding gives those tiny flaws room to exist without becoming disasters. It lowers stress everywhere, so imperfections don't get a chance to grow. Most failures don't start big, they start invisible. We also tend to think about loads as weight, but weight is only part of the story. Time is a load too. Every time a material is stressed, it changes, just a little. Repeated stress causes fatigue, even if each individual load is well below the limit. This is why paper clips break. You can bend a paper clip once, no problem. Bend it back and forth enough times, and suddenly it snaps. Not because the force was huge, but because time added up. The same thing happens to bridges, and planes, and machines. Temperature cycles matter too. Materials expand when they heat up. They contract when they cool down. Once? Fine. 1,000,000 times? Different story. So engineers don't just design for today. They design for decades of vibration, heat, cold, wind, and use. Overbuilding is how structures survive long enough for us to forget how close they ever were to failure. Time is a load engineers can't ignore. When efficient becomes fragile. Now here's the part that really flips the idea of efficiency. Designing something to be just enough leaves no room for error, no surprises, no misuse, no aging, no accidents. A perfectly optimized system works beautifully, right up until something unexpected happens. And something unexpected always happens. Overbuilding isn't about wasting material. It's about buying resilience. It's about slowing failure down, making it predictable, making it visible. A structure that's slightly overbuilt might crack before it collapses. It might sag. It might warn you. A structure that's perfectly optimized might fail instantly. From the outside, overbuilt designs look excessive. From the inside, they assume things will go wrong, and they plan for it. So the next time you see a massive bridge, a thick beam, or a machine that looks way stronger than it needs to be, that's an engineer saying, I don't trust the world to behave, and I'm designing for that. Because the goal isn't to survive the average day. The goal is to survive the worst one.